So we're here today to talk about discrete element method, or DEM modeling, and specifically the advantages in grain handling applications. So my name is Eric Peterson. I'm a principal and senior project manager at VAA, which is an engineering firm based in Minneapolis, and have about 30 years of experience in material handling equipment and equipment design and facility design. So you might be asking yourself, why does DEM matter? Well, what if you had a single tool that could de-bottleneck existing facilities, fix problematic grain handling installations, or prove new installs will work before construction and startup? Also reduce grain breakage and development or creation of dust at transfer points, possibly reduce overall stack-up heights, and give you a high return on investment by doing all of these things. Well, that's what DEM can do. And what is DEM? DEM is discrete element method, as mentioned. It's a numerical method to simulate the behavior of individual discrete particles that are in a simulation over time. So what that means is that you take a physics model and you use that with specialized software, and you can actually have the individual particles, but just like kernels of grain, behave with each other and with boundaries in a way using established physics models, using forces of gravity, other things, to get it to simulate real world behavior and of flow of materials. That's one way that it's used. So like I said, it tracks each particle position, its velocity and force. The screen on the left is from a simulation. A couple of things about the simulation: there's like a colored graph on the side that goes from, in this particular one, it's from 0 to 1,500 feet per minute. And the individual particles are colored based upon their speed or velocity. And you can see in this one, it's actually feeding into a bucket elevator. And it shows how that's feeding. So it's a screenshot from a video. So it tracks the particle position, the velocity, the force. It uses, like I said, well-established physics models in its calculations. Some of those physics models that are used have been around for over a century and are well tested and understood how different particles interact with each other when they hit each other and bounce off each other and commingle, as well as interact with boundaries like the inside of a spout or a belt on a belt conveyor. It utilizes the force of gravity as well as other forces like normal force, tangential, and adhesive or cohesive force, meaning how sticky are the particles to each other or to boundaries. And then how much does a particle want to roll? If you have a glass bead on a glass table and you tip that table even just a millimeter, that glass bead is going to roll off. That's an extremely low rolling resistance. Whereas if you have a really rough table and you put something that is kind of sticky, you can tip that table very far without that thing rolling off. So that would be a high rolling resistance, for example, which is a key element in DEM simulations. So the way it works is it analyzes and does an accurate replication of real-world behavior of bulk granular materials, for example, whole grains or grain byproducts, in a simulation. The first step in the workflow, a lot of times, when you're looking at an existing installation that's problematic, is to scan the existing area and using 3D modeling software like Autodesk Revit, for example. You can model up that existing situation, the existing spouting. A lot of times in existing facilities, there is not the benefit of good, accurate, as-built drawings of an installation. So doing the scan becomes very important. And then you take that model and you bring it into a specialized software that does discrete element method modeling. There's various softwares out there that do that. Once you have that model brought in, then you can inject the particles that you've set up in the software, that you've calibrated and set up to behave like whatever grain or whatever material you're handling. and then run simulations at various volumetric and tonnage flow rates, and then analyze the results by way of videos, screenshots, and checking on wear and different things like that. The screen on the left, or the image on the left there, is from one of those simulations. This is a before shot, meaning it is taken of the chute work and the belt loader. It's loading from one belt conveyor to another belt conveyor. And you can see there's a lot of spillage, a lot of kind of improper loading of that belt conveyor, and we'll see more about that later. So the way it works with the unique particles is that you go into the software and you have the capability of assigning the particle density, the individual weight of each particle, the size of the particle, the shape of the particle, its elastic properties, how squishy is it, the coefficients of friction, whether it be rolling friction that I described earlier, or just static friction or dynamic friction. And then you can assign similar properties to the surfaces that the particles interact with. And this includes, for example, rubber belting, lining material, whether it's ceramic or steel or stainless steel. You can assign the hardness and density and again, those coefficients of friction to actually replicate how that material behaves. Corn or other grains or grain byproducts, for example, will slide very differently on concrete, like a concrete bin bottom hopper versus a steel bin bottom hopper, or a stainless steel or ceramic tile. They all have different characteristics that allow for better or worse flow ability. This is that same belt conveyor, by the way, that I showed in the earlier picture. This is a view looking up the belt through a cross section. You can see in this particular one, we have the vectors turned on, which is why everything looks like a bunch of arrows. But you can see that it's spilling off of the sides of the belt and not hitting the loader very well. And we'll see more of that later as I go through some case studies. The way DEM is currently used in the grain industry, the first thing that it's been used for quite a while is design of specialty equipment. And this includes bucket elevators, where cups for bucket elevators are designed with the spacing of the cups, the speed of the head pulley, the shape of the cups. So manufacturers of bucket elevator cups are currently using this in their designs with various products to see how that behavior works. And this is a view of the head section of a bucket elevator showing kind of a snapshot of the material when it's static inside the cup. And then once it hits that centrifugal force across the top, it starts to spill out the cups and then gets fully emptied out prior to the material passing over the throat plate. It's also been used in grain sizing equipment like indent cylinders, where you can, design the specific indent shape and size and pattern on an indent cylinder, and the speed of the indent cylinder to separate various grains or sizes and grade of grains. It's been used in various mixing machine designs and so forth, where you're trying to figure out if the mixer is going to get a full mix versus partial mix by looking at how the particles interact with each other for commingling. Other uses that are much more prolific, or can be prolific, is the design of transfer points between material handling equipment. So this involves spouting, or sometimes called chute work, between one conveyor and another conveyor, or maybe between some conveyors and a bucket elevator, or a bin and a conveyor. It can involve custom designed flow splitters or dividers, where you're trying to split the flow from one source to two sources equally. You can also use it to design very shallow and tricky spouting runs that you couldn't really use conventionally. If you were to use the conventional rules of thumb on spouting with minimum slopes and minimum size spouts and large elbows and so forth, in an existing installation, you simply can't fit that in if you want to add a two-way valve off of an existing spout and go into another belt conveyor to go to a new bin or something. A lot of times the answer traditionally has been raise up the conveyor, which changes you have to lift the conveyor up. You've got to oftentimes have more horsepower with the conveyor, which affects shaft size and pulley size. You have to redo the structural around it, which can be very, very costly and invasive for an existing facility. So in some cases, you can look at an existing system and design a custom spout or chute that deviates from those rules of thumb, but is proven through the simulation to work. There's also custom flow aiding devices like flow retarders or dead boxes and baffles that can be put into the simulation to change the behavior of the flow and do it on the computer before you actually put grain through it. And all of those things, when you do it in the design phase and on the computer prior to actually welding up steel and installing conveyors and installing chute work, is much more cost effective and much less invasive than doing it through a trial and error basis after startup, trying to get a system to operate according to its original design intent. We see a lot of facilities that have been running for sometimes decades with bucket elevators that have only ever been able to be filled 60% full or 70% full because they're being loaded poorly. Same thing with belt conveyors, for example. So this is the same, you can see on the picture on the left, it's just a screenshot from a 3D model of some finished spouting designs. And this is a screenshot of that spouting design after it's been detailed, brought into the simulation software and running the simulated flow through it. The other thing you can do with DEM is you can optimize wear liners. I mean, we often put much more wear liners, or surface is much a greater percentage of the surface of spouting is lined than actually needs to be lined because, for instance, we all know, or many of us know, it's been well established that as on a long spouting run, as the grain speeds up because of gravity and velocity and reaches closer and closer to that terminal velocity, the pile that might have been very high in the spout, even after 4 or 5 feet, can cut down to half the spout height. And as you continue to speed up, it cuts down and down and down. And on a long rectangular spout, you're only having, maybe it's a 30-inch tall spout, maybe there's only 2 or 3 inches of grain sitting in the bottom of that spout, speeding down before it hits an elbow. So there's a lot of wasted structural steel and wasted plate steel and chute work that could be optimized. And this has been known for a long time and has been done successfully on a case-by-case basis, but people still generally use the overall rules of thumb that are based on grain in a dead stop condition. So when you see it in the simulation in a situation like this, you can even see areas that just don't need lining because of how the grain is flowing through there and where it's stopping and changing directions. And you can optimize lining by only lining the areas that actually need it. And you can also look at areas that are getting impacted much more than others and do a custom liner there, maybe a more exotic liner like a chromium carbide overlay versus a UHMW or a ceramic or something like that. And then just the directional changes of feeding a belt conveyor or bucket elevator. When you're feeding at right angles, sometimes in a lot of facilities, the most optimum layout initially looks to be feeding a bucket elevator from the side. You're coming up and you're hitting the end and then you're having to turn directions. And that might make the most sense for the overall layout of the facility. Same thing with belt conveyors. Maybe you're feeding it at a right angle or even a twisted angle. That might make a lot of sense for the layout. But those inherently create problematic loading conditions for those follow-on pieces of equipment, like the bucket elevator or the lower conveyor. And to get those things right, a lot of times what happens is you start it up and it's causing belt tracking issues, and then you have to go in and maybe weld in some baffle plates after startup. It's hot work. It's that portion of the facility is shut down at the end of a project when an owner or operator is really desirous of having the facility running. Now you have to schedule a shutdown and weld in some plates and try it again. Maybe it works, maybe it doesn't, and then you're doing it again. And oftentimes people just give up after a time and just run at a reduced rate. So this will allow you to eliminate that from the equation, get it right the first time, and avoid those those costly startup fixes, the trial and error fixes. It also has the ability to reduce the cross-sectional area of spouts. As I mentioned before, the spouting rules of thumb, most people know, are invariably conservative, especially as you have long spouting runs. And they're designed that way because of choke points. When you have choke points where grain is hitting one elbow and changing direction, it's at the elbows where you're having the choke points. Particularly true when you start getting into byproducts like soybean meal or DDGS or others that have a more cohesiveness to them, or a stickiness, and are less flowable or not as free flowing as whole grains. And so if you design all the spouting that way, then you're wasting a lot of sheet metal. The other thing that can be done is you can design maybe a little bit more gentler elbow that helps that change in direction with some of those products, and then reduce your overall spouting sizes and optimize the design. And by doing that, you're minimizing or reducing the entrained air that's coming with that grain, which helps with dust control by reducing the amount of dust that's being generated, not only by gentler handling of the material through elbows, but also by shutting off some of that blank space within the spout and reducing that. Here you can see on the left is an example of an elbow that's going into a spout that actually has an internal directional spoon in it. This is handling soybean meal at 40,000 bushels an hour. The spoon, you can see, it actually takes the soybean meal and it hits the spoon, and then it curves down. And the curve is based upon the velocity of the material coming in, what that material kind of naturally wants to follow a curve. If the spoon wasn't there, it would hit the sidewall and it would boil back and kind of collect on the far sidewall there, and then the material would carve a curve through that boiled back and stagnant material. And so you kind of use that to design the curve of the spoon. And then, as you can see there with that graph of 0 to 2,000 feet a minute, the color of the material as it's going into the spoon and as it's through the spoon and leaving the spoon is fairly uniform. And that's a good indication that you're controlling that without generating a bunch of impact-related dust on that change in direction, and then having the ability to move that material without having it bunch up in a much smaller spout than is traditionally used. So this particular spouting with the curve, instead of using the 65 to 75 bushels per hour per square inch, it's with soybean meal on 45-degree spout. And I think it was at about 120 to 130 bushels per hour per square inch, which conventional wisdom would say that's way too small of a spout. But by handling that change in direction in a different way, you're able to reduce the spouting sizes. And then the vertical spouting is not lined because we're able to control that with that spoon and really have no wear impacts on the vertical spout or the transition leading to the vertical. Here you can see a curved belt. This is on an air-supported belt conveyor, which is even more finicky when it comes to loading. You have to load those from the first kernel all the way to your full capacity. To make those work right, you have to load it consistently in the center all the time. What you're seeing in the background is a graph. So you see the red and the blue there. This is not political, by the way, but the red and the blue are 50-50 split of the material on that belt. So as you can see on the graph, the lines are overlapping all the way up, and then they have kind of two irregular heartbeats of that material as it passes through a strata on the belt, very much overlapped with each other with a very, very central loaded configuration. In this particular one, startup, we set the spoon where it was supposed to be, feeding this belt, and then ran it, and it ran perfectly without any issues, without any tracking issues or washing of the air belt to one side or the other. So other benefits is increasing capacity of existing systems. Like I mentioned before, if problematic loading is forcing you to run at 70% speed and you can only receive so many trucks per day or ship so many vessels per year, Obviously, maximizing the throughput capacity can shorten the time it takes to receive a truck or load a ship or load a rail car. And that can also be used to decrease capital costs of new projects by a reduction of stack-up heights. You can use more, less conventional spouting wisdom, maybe more shallower spouts that are handling the changes in direction a little bit carefully, that can actually result in a lower stack up. And we'll show some examples of that in a minute. And then lower maintenance burden. If you're loading belts properly, you're not going to have belt tracking issues. You're not going to have as much stress on your idlers, on your belting itself. Improper wear or wear that happens too quickly on bucket elevator cups on one side of a bucket elevator versus another. And then no costly field fixes during startup. So the new case study number 1 was a new build. You can see here, there's a belt conveyor at the top. It goes off, the material goes off the end of the belt conveyor, goes down through the transition into a splitter valve. The splitter valve is actually twisted at about 25 degrees to shorten the stack up even more. And then the 2 chutes actually feed 2 drag chain conveyors that are mounted on the roof of the silos. So it's taking 90,000 or 80 to 90,000 bushels per hour of soybean meal that this can handle, and it's splitting it 50-50. And then that material is going into the 2 drag conveyors, and the spouting is less than, I think that the shallowest we went here was 40 degrees on the spouting, but it scrunched that layout from feeding from a belt conveyor to splitting down on the drag conveyors and getting those drag conveyors to feed some very large silos through multiple discharges. The conventional way of doing the spouting would be to have, a tall transition here and then a 2-way valve, or maybe the shuttle valve is turned, in line with the conveyor, perpendicular to conveyor, using a 50-degree spout, much larger spouts with dead boxes and so forth, and would drive the stack up height a lot. We're talking, at least 10 feet or 15 feet, which pushes the belt conveyor out further because you need more distance to continue that incline to get to that height differential. So the project goals was to reduce the stack up height. And again, this was a new project. So minimize the stack up height between the belt and the 2 drag conveyors feeding the silos. And then also split the flow evenly and prove out that it's split evenly. And then verify soybean meal will pass through shallower spouts and into the drag conveyors and feed through the upper chain return of the drag conveyors. So I'm going to show a couple simulation videos. And this is a video of that, where that screenshot came from. You can see the materials are being fed onto the belt, injected into the simulation, and then based upon the actual belt speed of the belt from the design, goes through the shuttle valve or the splitter valve, and then has the material kind of splitting and going off in 2 different directions. And it goes from the belt conveyor to the 2 different drag conveyors that are sitting in parallel with each other on the roof of the silos. There's another view of this where we're kind of looking straight on the shuttle valve. And as this thing refreshes and replays, pay attention to the center of the shuttle valve. You'll see the shuttle move prior to the grain hitting it. And what that is we moved the shuttle within the simulation to find out exactly how far off center it needed to be. Because again, this valve is twisted in 25 degrees in plan view. And having it right in the center did have an unequal flow through the chutes. So we used the simulation to figure out that it needed to be 7.1 inches off of center. And then that gave us a premium or optimum 50-50 split between the 2 chutes on the bottom of the shuttle valve and feeding into the conveyors. And the other thing we did was we looked at the feed of the material from the shuttle valve into a drag conveyor and ran the chains at the speed that the chains are moving in the drag conveyor. This is a double chain drag, 40,000 bushels per hour for soybean meal. and making sure that the material wouldn't choke up in the spouting and it would flow nicely through the chains. Then another view of that simulation. This is looking at a cross section through the drag. The drag conveyor itself mostly is turned off or hidden, but you can see the hogbacks or the inverted V's here that protect the chains that are coming back. You can also see a little gap in here. There's a little divider plate in the drag conveyor that keeps the chains from kind of interlocking with each other, or the paddles from interlocking with each other. So one of the things we tried to do here was make sure that we were hitting, as we first feed that it was hitting right on the center of the conveyor. You can see there, the first material is hitting that divider right in the center. And then as it continues to fill, it just kind of heaps up over the two hogbacks, which we changed the initial design of the loader to provide more space for the material to flow around the hogbacks and around the chains by way of simulating, making sure that we had enough room for all that flow through there. And then this is a graph that shows the split flow from 90,000 or 80,000 bushels per hour to 40,000. And then when we started up the facility, we went out and made sure the shuttle valve was moved that 7.1 inch within the valve itself, and then used that as your initial startup calibration. And then when we ran the grain or the soybean meal, in this case, through the upper conveyor, through the shuttle valve, and then through the drag conveyors, we started with about 10,000 bushels per hour and then ramped it up to about 20, and then 50 or 60, somewhere in there, and then eventually got up to about 95,000 bushels per hour, I believe, is what we were running through it. But that we checked to make sure that the split was even. We checked the amp meters on the motors. So as we continued to fill up the drag conveyors, the amp meters on the motors climbed at the same rate at the same time. We also took some visual inspections through inspection doors and saw the bed depth increasing uniformly on there through the drag conveyor. So that initial setting in the simulation ended up being exactly what the setting was for an even split in real life. So project goals met. Lower overall cost of construction. By shortening that stack up, we were able to keep the new silos within the existing plant road and away from the existing drainage pond. And part of that plant road is a lot of the site utilities run right alongside that existing plant road, including the fire loop and the various other utilities. And so it would have been a very, very costly civil project to move that plant road and then redo the drainage pond. This is a facility in a urban area with a lot of environmental oversight. And so moving that drainage pond and changing that stormwater pollution prevention plan would have been a very, very large and costly and painful undertaking. So that all allowed us to keep within the plant road, and then we didn't have to do any of that. It also shortened the structures needed at the top of the silos. It shortened the conveyors that transfer and feed over to the silos and come back from the silos, got to be shorter, along with the bridges that support those conveyors, which has a trickle-down effect on the horsepower of the motors and so on and so forth. We were also able to target which areas needed to have more exotic lining. We used a vacuum bonded ceramic lining on certain portions of the inside of the shuttle valve, and other portions we just used regular ceramic, and others we just left unlined because they really didn't need any lining. And again, kind of a common theme is eliminating the costly site work or costly field fixes, during startup. This startup was at a facility that was, when it was originally built, similar installations took a lot of trial and error, a lot of welding of baffle plates and coming up with weighted baffles and so forth to load conveyors properly. And that took many, many months to get that right after startup and after they were looking to operate the facility. And so they were kind of limping along, had to schedule shutdowns. Then you could do some trial and error work and try again until eventually they found solutions. But it's very, very costly and time consuming. For this startup, it took a few hours, and there was no costly trial and error welding and baffle plates after the fact. Case study number 2. This one is an existing installation, and the picture on the left is the existing spout chute work and 2 bucket elevators side by side. So it's kind of an older design grain elevator where you have a single drag conveyor that is split, or the idea is to split it and have 40,000 bushels an hour split to 2 bucket elevators at 20,000 bushels an hour. The way that it's laid out with the spouting is causing, or was causing, side loading of the bucket elevators. You can see the little screenshot from the simulation here. That's how the grain looks when it's going into the bucket elevator, kind of what I call what the bucket elevator cups see. So these legs had 2 cups. So one of the cups was getting overfilled, the other one was not getting filled enough. And because it was so imbalanced, they weren't even really able to benefit from the boot filling and kind of making up for that improper loading by scooping the boot. The boot was filling and kind of leading to one side and causing wear on the one side. So they were only able to receive about 70% of the initial design capacity, which reduced the number of trucks they could receive at the facility through this system. So the goals were to fix all of that, increase the capacity of the bucket elevators by splitting the flow evenly into both and feeding the bucket elevators both uniformly. And then also we took a look at the speed of the bucket elevator at the head pulley with the cups that they're using and optimized that speed to go a little bit slower and prevent the backlegging that they were experiencing. So for that simulation, we have some videos. This is a video of the original condition, or what the existing condition was prior to the changes. And you can see the grain is coming through the custom built hopper or transition from the drag conveyor. Has the gates, you can kind of see one gate is sloped at about a 45 degree. The other one is shallower. The reason why it's this way and why this hopper is unequal is because there's a drive for the motor of the drag conveyor right here. So as they put this together, they realized, well, we got to drop this one down, and it caused an unequal loading condition. And then obviously the loading into the side of the legs, just like was shown in the previous one, is causing issues, or was. This is another view of the existing, kind of showing how it's coming through there. And from this view, you can see how much it's hugging the sides of the bucket elevator and causing that improper loading. And they have another conveyor from Reclaim that feeds the same system, but effectively has the exact same behavior. So this is a view of the fix. And in this view, you can see we have the one gate closed, but you get the idea. The feed going into here is split more evenly. And then we have a different style elbow where it's changing directions. We also pulled the whole hopper toward us to get a sloped spout going into the bucket elevator and more of a uniform feed. We also have a box that has some internal adjustable baffles to kind of tweak the center point of the flow as it hits the bucket elevator. And this is what it looks like, or what the cups see, as I said before, what it looks like going into the bucket elevator. So much more uniform, much more consistent, kind of a level pile going in there and feeding the cups very nicely. So results, project goals met, has the ability to receive about 30% more by feeding things more uniformly and splitting the flow evenly. The wear on the bucket elevators, both the housing of the boot as well as the premature wear on the one side of the bucket elevator cups, no longer an issue. Belt tracking issues are no longer the case because of the uniform feeding. All those things with the goals met. Case study 3, this is a large belt conveyor that handles about 80,000 bushels per hour, feeds another belt conveyor at about 80,000 bushels an hour. Currently, what they're experiencing is the load on the belt is pushing the belt off to the side. They've had to trim on a 60-inch belt. They've had to trim it down to 57 inches wide, and they've had to tweak the pulleys to get it so that the belt is virtually touching the rub blocks on the one side when it's running empty. And then when you load the belt with the grain and it pushes it over, it's tweaked enough and trimmed enough so that when it pushes it over, it does not hit the rub blocks on the other side of the belt and shut down the belt. But that invariably causes more spillage on the side that it moved away from the housing and so forth. This particular screenshot is showing the existing condition. Again, we've in the simulation turned the skirt boards off, or basically made it so that the grain particles don't see the skirt boards at all. And we did that so that we could kind of see what the worst case scenario behavior is without skirts, because it tells us how the grain is behaving and does not invariably trick us with the skirt boards handling a lot of the spillage, which is what they're doing right now. And they're basically holding back a dam of material and wearing out very, very quickly. And they're not able to do the job very effectively, and they're not doing the job they're really intended for, which is just minor kernel spillage. So we wanted to load the belt more gently and on center, fix the alignment and tracking issues. By doing this, increase the capacity that the belt can handle, and then also design the chute work to handle grains and byproducts. So the simulation videos here, this is a view of the existing installation, and you can see the grain comes in and it trajectory hits the sidewall. We started all these simulations at 20,000 bushels an hour, and then we ramped up to 40,000, as you saw just there. Then we go to 60,000, then 80,000. You kind of see the behavior at those different capacities. This particular system gets surges of grain. It'll get a trickle and then a big surge. So seeing that variability of the grain as it goes at different capacities was important in this case. But we also look at that from the standpoint of making sure that at different capacities, you're filling that belt properly all the time, which in this case, it's really not. So hitting the sidewall, it's kicking back, it's hugging the one side, causing a lot of spillage on that side, also causing the belt to sweep over to the side. Another view of that, looking up the belt, the lower belt. And this one has vectors turned on in the simulation. And what that really means is it's showing the translational velocity or the translational movement or horizontal movement of the material in addition to the vertical by way of kind of turning the particles into arrows. So you can see it's kind of wanting to hug this one back side. As I pause it here and roll this back, as the material is first entering in, it's really wanting to hug that one side. And what it does as it comes in and hits this is it's sweeping off clockwise to the left. And it's actually pushing, that's the direction the belt is moving, and it's hitting the rub blocks over here. So that's why they had to trim 3 inches off the belt and then kind of get the belt torqued over to one side when it's running empty prior to loading the material onto it. And this again, the skirt board's being turned off so we can kind of see the behavior. At 20,000 bushels an hour, that behavior, you can see the spillage that's happening or the amount of force and material that's wanting to get past that skirt board. And does get past the skirt board in a lot of cases because of the skirt's wearing out. And then as we increase to 40 and then 60, we start to get even more spillage. And then once we get into 80,000 bushels an hour, we get a lot of spillage on the far side because it fills up that loader more. And then now we're having just a lot of spillage through that area. So that's where the skirts are having to do a lot of heavy lifting that they really shouldn't have to do with a properly designed loader and system. And you can see this is a 50-50 split graph showing how much unbalance is happening on the loader. This is a video that shows upstream or downstream of the loader, further up, what the grain looks like from a 50-50 split standpoint. You can see it's very imbalanced. Kind of a concave negative surcharge angle, which is not ideal. And then on the solution, this is what the graph looks like with the solution design. So you can see the left right is very much on top of each other at the 20, 40, 60, and 80,000 bushel per hour marks. Very uniform and very consistent. So here's a video of the cross section of the belt looking up. You know, as the direction of the grain goes, you can see the initial 20,000 bushels an hour load is very uniform from the first kernels up to, you know, the pile. And as you jump from 20 to 40, you can see it continues to grow. We've got a nice, you know, curved surcharge angle there, a nice hump of grain centered on the belt. And as it goes to 60,000, it continues to grow. And then 80,000, it grows uniformly in the same way as we get to the end of this simulation. So very much what an ideal belt loading situation is: a nice heaped pile, draws the edges of the pile away from the edges of the belt, minimizing spillage and so forth. So that just kind of shows how that works. Here is a video showing a side-by-side. The one on the left is the existing condition. The one on the right is the new condition. On the one on the right, you can see an internal directional change spoon was put into the head section in the simulation to help change that direction and more gently handle the grain as it goes off the head pulley and then starts to travel vertically. The spoon also tapers in on the side to kind of grab and corral that material into more of a smaller footprint as it hits the spout. And then the spout is much longer. It's not vertical like it was, and it changes the direction in line with the conveyor. The spout is also a lot narrower, a lot smaller in terms of cross-sectional area, and it's curved on the bottom, or chamfered on the bottom, as it curves forward, and that allows the material to sort of be cradled as it drops down onto the belt. And then another view of this side by side. And in both of these views, by the way, the skirting is still turned off. So we did that to kind of see with the more optimum loader design. You can see there's still spillage on the outside, but with the skirt boards close to the edge of the belt margin, like they're usually designed, we'll prevent that minor spillage. And that's really what they're intended for. When it comes to the situation on the left, again, they're having to do much more work than they're really designed for. And as you increase the capacity to get up to the design capacity of 80,000, that's minor spillage that happens on the right starts to go away to almost nothing. So the case study number 3, the results and benefits, the project goals being met. Reducing dust generation by using a smaller cross-sectional area of the spout, by more gentle handling of the grain as it goes, or the soybean meal or grain as it goes off the head pulley. Less severe impact points throughout that spouting line, not impacting the belt as severely, which would reduce the dust generation as well as the grain breakage and wear on the belt. Also reducing the demand on the skirting, which is very important. And then optimizing the wear liners. The spouting where we have the impact zone is going to be using a chromium carbide overlay liner, which is a more expensive liner, but certainly has much more longevity to it, but kind of focusing the liners really where they're needed. And the entire head box will be unlined because the only area that needs the lining is the spoon itself. And then no costly field fixes during startup. So in summary, discrete element method modeling, or DEM, can help de-bottleneck existing facilities. It can help fix some problematic grain handling installations. It can also prove new installs will work before construction and startup, avoiding those costly, fixes, field fixes. You can also use it to reduce grain breakage by a more gentle handling of the grain in the design phase, and then lower stack up heights, which, as we saw, can have a big impact on project costs and other implications. And then it has a very high return on investment. The software is expensive and it does cost a little bit of money to go through these things, but you can see the benefits by not having the very costly changes that have to happen in the field, or reducing the overall cost of construction by lowering stack up heights. And some of the examples I said where they didn't have to mess with the existing drainage pond or reroute a plant road and a bunch of utilities. Obviously, that's money in your pocket that more than offsets the cost of doing the simulations in advance.